Santa Barbara and joined Harvard as a junior fellow. Shortly after that, he decided to stay at Harvard as a professor and got his tenure in a very impressive 3 years. He has a long list of awards, including a Sloan and South Korea Johannes Gutenberg Award. He's a fellow of the APS. He's won the Siemens Award. He's a distinguished scholar at the Max Planck Institute for Quantum Optics, a Humboldt Research Award, and a Simons Fellow. So today, Eugene will talk about superconductors out of equilibrium, I think. So please.
Thank you, David. It's a pleasure to be here. Thank you for this introduction. So I'll talk about non-equilibrium.
Could you make sure your mic's on? Yeah, that mic. Perfect.
Okay, can you hear me now? Right, so it's a pleasure to be here. Thanks for the invitation. I had great discussions earlier today. Learned a lot, very stimulating. So I'll tell you some of the work we have been doing, and that actually sort of covers kind of an extended period of time. So some of the things go back to, say, when David was still at Harvard, and some of the work was done with Ehud and Anatoly when they were postdocs. And then I also talk about more recent work, which was primarily done by Mertas, Babadi, and Fabian Grust. And I will also point out connections of the work that we're doing theoretically with experiments, and a lot of what we have done was done in collaboration or was directly stimulated by kind of the groups of Emanuel Bloch, Markus Greiner, and Jörg Schmidmeier. So, okay, oops, sorry, for some reason it's not. Okay, sorry, somehow my computer just froze. Sorry, I think I may need some help here.
This is Windows.
Yes. Okay. Okay. Sorry. Apologize. Somehow maybe switching. Just completely froze the first time it happened. Completely stuck.
Just restart.
I'm trying to just not responding to any buttons. You can control delete.
It's frozen, right?
Yes. I tried. Okay. Oh, okay. It needs an experimentalist touch. Thank you. That's Jeremy.
Exactly the same computer. This
Okay.
happened to me once on this computer.
Oh, it happened to you. Okay. see. Does it? Okay. Seems alive. Okay. Right. So let me just start with an introduction. So the talk is about non-equilibrium, and this is something that, of course, you know from your basic classes on quantum mechanics. The simplest example would be Landau-Zener problem when we have two levels going through an avoided crossing, and back in the 30s, people understood how to solve this problem essentially exactly. But once we increase the complexity of the systems, when we start looking at many-body systems, let's say when we look at collisions of heavy ions and formation of quark-gluon plasma, or even look at something even more exotic, such as our universe, which is also a non-equilibrium quantum system, dynamical problem, quantum many-body systems out of equilibrium are much harder to describe. And this is not just a question of academic curiosity, it also has some practical implications. So for example, one of the interesting kind of problems at the intersection of, again, optical academic research and applications is optical transistors, when one wants to take photons to the level of single photon nonlinearities, and then one really has to solve non-equilibrium problems, since for photons calculating the ground state doesn't really make sense. On the other hand, it's kind of, when we think about condensed matter physics, this is not the type of problems that we're used to. Like a usual condensed matter system is kind of piece of materials. We're interested in the state of electrons, and electrons are very well equilibrated with phonons, which provide a bath. And so we can talk about equilibrium phase diagrams, or we're interested in response functions in an equilibrium state. So however, this paradigm, I think, has been changing in the last few years, and this is a combination of factors. We have seen very rapid development in the field of pump and probe, or dynamical manipulation of states of matter. We have seen progress in realizing these kind of synthetic materials, or kind of quantum simulators, such as atoms and molecules in optical lattices, which are very well isolated from the environment, so there is no bath that helps to the system to relax. Or again, as I mentioned, nonlinear photonics is another kind of interesting direction, which strongly drives kind of the field of non-equilibrium many-body physics. And intrinsically, non-equilibrium problems are much harder. So if we think about truly many-body systems, okay, we know that we're dealing with macroscopic numbers, like Avogadro number of particles. But then when we think about equilibrium, or sort of dynamics close to equilibrium, this is typically a very tiny fraction of the entire Hilbert space. So it only grows polynomially with the system size. Whereas when we talk about the entire Hilbert space, then it actually grows exponentially with already a large number. And therefore, you know, when we take the system out of equilibrium, we cannot a priori say whether the system will explore all the possible states, or we can still limit ourselves to sort of a subset of relative states. So we have to deal with the issues of large number of states involved. We don't have efficient descriptions, but perhaps even more importantly, it's very hard to characterize states which are not in true equilibrium, when we cannot think about concepts as order parameter, right, spontaneous symmetry breaking. So at least the way I think about it is that if we think about, say, non-equilibrium classical physics, right, nonlinear equations, then we have many universal paradigms. So for example, we know that we can have soliton formation, we can have pattern formation, such as Bernard-Selson systems where you have a heat flow. Or when we take quantum many-body systems, but in equilibrium, then again we have paradigms, such as broken symmetries, or something more subtle, such as Fermi-liquid theory, or even more exotic topological states. But we know that we can classify all of the states within one of these global paradigms. But when we try to bring together non-equilibrium dynamics and many-body quantum systems, the question that we face is it's not yet clear whether there is truly emergent universal behavior. right? Whether we have to analyze system on a case-by-case basis, or again, we can divide all behaviors into some universal classes and say that all kind of phenomena belong to this or that class. Well, and obviously the reason physics is interesting to us is of universality. So again, this is kind of my favorite example of universal behavior in physics. So this is something that goes back to David's work. So this is a story of the Higgs excitation. So I'm sure you all remember the Higgs resonance observed at LHC. So this is this peak, so it's proton-proton collision, and there is this peak in cross-section corresponds to the resonant energy which matches the Higgs excitation. And in order to see this resonance, experiments had to be done at energy scales which are 12 orders of magnitude larger than the room temperature. And actually, within a week of this announcement of the Higgs boson in high-energy physics, there was an experimental, the paper with experimental measurements of the Higgs excitation in ultracold atoms and optical lattices came out. So this was experimental work by the Max Planck group with theoretical work by David. And in order to see Higgs excitation in ultracold atoms, experiments had to be done at energy scales which were 12 orders of magnitude smaller than room temperature. So we talk about energies which differ by 24 orders of magnitude. However, the physics is the same, right? We can talk about universality of physical laws. So here we talk about symmetry breaking, and once you have a Mexican head potential, you have a Higgs excitation. So this suggests that even in dynamics, even though we talk about very different phenomena, we hope to find some truly universal paradigms, truly universal phenomena. And even at this point, as I said, I don't think we have this coherent picture. We have bits and pieces. And so that's what I'll try to do in this talk. I'll tell you about a few examples that we were working on, trying to sort of bring them from different areas of physics. But the goal is that by understanding specific phenomena, we hope to eventually see a coherent picture and sort of define a more universal types of behavior. So here I try to bring examples, again, from different areas of physics. So the first one will be traditional solid-state physics. So this will be a discussion of how we can dynamically get a state of matter that in equilibrium can only be realized at extremely, in very different conditions. So like superconductivity, which exists at low temperature, can actually be found at very high temperature. Then I'll talk about kind of very interesting non-equilibrium prethermalized state that has been realized with ultracold atoms. And actually, this study was directly motivated by the work done in high-energy physics and by sort of behavior observed in quark-gluon plasma. And then the last part, I'll talk about dynamics as a probe of things which have been discussed in traditional solid-state physics. So specifically, this will be an idea of analogies between QCD, between the Polaron model of particles, kind of like as nucleons can be thought of as bound states of, or mesons can be thought of bound states of quarks, and how this can be connected to excitations of the Fermi Hubbard model. And this, again, I think many of these ideas can now be tested using non-equilibrium dynamics and using the tools of atomic physics. Okay, so let me start by talking about dynamical control of matter. And so it's based on this theoretical work, but it really is motivated by experiments done by the group of Andrea Cavalieri on non-equilibrium superconductivity in buckyballs. So this is actually just one example of this type of experiments. People talk about optical manipulation of various charge and spin density wave state, Mott insulators. Also for superconductivity, people talk about, again, photo-induced superconductivity for, in the case of high temperature superconductors. I'll just focus on this because at least here we believe that we understand the equilibrium superconductivity. So it's a better starting point. So let me give you the key facts of the experiment. So this is buckyball superconductor, and this shows you optical measurements in equilibrium. You can see that in the normal state, sigma 1 is fine at a small frequency. Once the material becomes superconducting, there is a gap. Then the imaginary part of the conductivity, again, develops a very peculiar 1 over omega tail in the superconducting state. So that, and the prefactor is just the superfluid density. So these are kind of, so that just follows from the fact that if you have superfluidity, then instead of the Ohm's law, you see that your current can be accelerated by the electric field, which immediately translates into this relation. So this kind of relation are supposed to be defining features of superconductivity, 0 in real part of conductivity and 1 over omega in imaginary part of the conductivity. And as we said, equilibrium TC is about 20 Kelvin for this material. But what this group has found was that if they shine terahertz light on this, then instead of just heating this simple up, which should suppress superconductivity, they start enhancing it. You can see that this is already above the equilibrium TC. There is a gap opening up in sigma 1, and we have 1 over omega tail in imaginary part of the conductivity. Then they go to very high temperature, right? It's now 5 times larger than the equilibrium TC. There is a gap, right, in real part of sigma, and there is 1 over omega tail in sigma 2. So this phenomenon is really related to phonons. This is known from the fact that, okay, light has to be resonant with the phonon excitations in these materials. And it's a transient phenomenon. So this is the pulse, this red line, and this blue line shows the changes in the real part of the conductivity. So we see that kind of superconductivity gets enhanced, but then it disappears. So it's not a steady state. Okay, so okay, and this is like important because in principle people discussed previously how non-equilibrium can be used to enhance superconductivity through non-equilibrium state of quasi-particles. So it's the so-called Wyatt-Dime effect. In Russia it was known as the Eliashberg effect because Eliashberg explained it. But in this Wyatt-Dime Eliashberg effect occurs at very different frequencies. So this has to do with the gap rather than with the frequency of phonons. So it's very different physics. So let me start by giving you the usual argument why people believe that non-equilibrium, you cannot enhance superconductivity by making a non-equilibrium state of phonons. So let's go back to our usual kind of perturbative calculation of how do we induce electron-electron attraction through phonons. So think of two electrons exchanging a phonon. So we have electron momentum k, which sends a phonon, right, which gets absorbed by the second electron. So it's a second-order perturbation theory. So if we think about this process, we have matrix elements squared. There is energy denominator, and our initial state, right, is electron at momentum k. Our intermediate state is electron at momentum p plus an extra phonon. And then you can say, oh, if I already have phonons in my system, then I can benefit from the Bose enhancement factor, right? Now, if I think about electrons near the Fermi surface, which is what we usually do in BCR theory, let me just forget about the electron energies. So I have this coupling, electron-phonon coupling squared divided by the phonon frequency, and I have Bose enhancement. Okay, it looks like having a large number of phonons is good. But if you have a finite number of phonons, then we also need to consider another process in which we do not just emit an extra phonon, but we also absorb a phonon which is already present in the system. And then, again, in the spirit of the second perturbation theory, we have to look at an intermediate state, at the initial state, okay, which has 1 electron, intermediate state, which has 1 less phonon, right? That's why the phonon energy comes with a minus sign. Again, if we neglect the energies of quasi-particles, we see that this now gets, looks like a repulsion between electrons mediated by phonons, and it comes with the Bose occupation number for phonons. So if we add the two together, we find that effective interaction is still unaffected by the number of phonons that we have in the system, and that's why there is this argument that real phonons don't matter. What really matters for effective electron-electron interaction are virtual phonons, so you cannot enhance interaction by making a non-equilibrium state of phonons. Okay, so let's try to find a way to get around this constraint. So for this, let me at first kind of suggest a certain toy model without really justifying where it comes from. I'll explain it to you later. Let me consider phonons which are parametrically driven. So if we think about phonons as harmonic oscillators, right, you can recognize the usual harmonic oscillator. This is a spring constant, but it's now a time-dependent spring constant. And now what we want to ask is, well, can we calculate how this non-equilibrium state of phonons, right, phonons which have been parametrically excited, how do they mediate effective attraction between electrons? So we know how to calculate it when phonons are in equilibrium. How do we generalize it? So there is actually a very simple argument which can be understood, which you can formulate like this without doing calculation, that effective interaction between electrons mediated by phonons is nothing but the response function of the phonon system, regardless of whatever state they're in, right? So, okay, so in this case, right, this is the usual retarded correlation function for the phonon displacement operator. So how do we explain this? Well, okay, I'll just give you, again, a heuristic argument. You can make it more rigorous. Think about a harmonic oscillator, right? Q is a displacement of harmonic oscillator, and we couple it to an external field. Now, we know that this external field will cause a displacement, right, of the position of the harmonic oscillator, which is proportional to the field. And then we have response function, and it's the same response function which comes into the fluctuation, right, into the fluctuation describing kind of time-dependent fluctuations in the system. That's fluctuation dissipation theory. But it also tells us that this is how much the system will lower its energy in response to the applied external field, that the prefactor is controlled by the same kind of susceptibility, which is the same response function. And now if we think about electron-phonon interaction from the point of view of the phonon, so this is displacement field of a phonon, electron density acts exactly like an external field. Therefore, you can immediately conclude also, if this is my external field, if I integrate out phonons, I get effective lowering of the energy by the amount which is proportional to external field, which is square of electron density. And the prefactor should be just response function of the phonons. And so the new problem for us is just calculate response function of phonons when they're driven out of equilibrium. Well, actually, this problem with phonons which are parametrically excited is not too bad, because it's still a linear problem. You can write classical equations of motion, right? Again, time derivative of displacement is just momentum. Time derivative of momentum is determined by the spring constant and position and displacement. But now the spring constant is time dependent. So you can integrate this out and just relate displacement at later times, let's say to momentum and displacement at earlier times. And these are some kind of propagation kernels. What is crucial now is that these equations of motion are linear, right? So it doesn't matter what's the initial state that I have. I will always get relation between displacement at later time and earlier times is the same. It's just determined by the Hamiltonian rather than by the state. And now if I want to calculate correlation function, right, which determines my effective electron interaction, you can see that, because we wanted this displacement at later time, but I can relate it to a momentum at earlier time when this commutation relation is just 1. So somehow this correlation function is entirely this kind of this propagator, right? Something that is determined by the non-equilibrium Hamiltonianness of phonons, but not by the initial state of the phonons. So we see now the difference with this argument that well, consistency with arguments that we gave before. The state of the phonons doesn't really matter. What matters is that we're actually driving the phonons, that they actually obey not the usual static Hamiltonian, but the out of equilibrium phonon. And now it's really this response function which will determine what will be the effective strength of effective interaction between electrons. Well, these are harmonic oscillators, right? Even in the case of parametric drive, you can solve it exactly. We can calculate what's the effective interaction. And we know that when we drive close to the resonance, we expect everything to be enhanced, including the response function. And indeed, let's say if we do perturbation theory, we have enhancement of the average effective interaction. Interestingly, we also, because of course, we apply kind of this periodically field, which is periodically oscillating. Our interaction is not constant in time, it's oscillating. But in fact, it's even good news for us, because even if you do naive calculation, TC is a very nonlinear function of effective interaction. So averaging of the exponent of the time-dependent interaction is not the same as averaging interaction itself. We gain much more on enhancing interaction than we lose on suppression. So both the average increase of the interaction and the fact that we now get oscillations in the interaction should work in our favor. So qualitatively, then, you can think about the argument that I gave you the following way. So often, when we think about kind of trying to get superconductivity, we try to tune ourselves to the vicinity of a quantum critical point, right? The argument is, okay, sorry, just to remind you that we had this effective interaction, right, which was set electron-phonon coupling constant divided by the phonon frequency. So you can say that by coming close to, let's say, this phase transition with the CDW phase, we make the phonon frequency smaller, and this gives rise to enhanced electron-phonon interaction, right? So in a kind of cartoon way, you can say that we're doing something very similar. So if you take harmonic oscillate and you start parametrically driving it, then you can actually, with weak damping, you can make it completely unstable, right? So it's also kind of a way of making the phonon soft. So therefore, what we're describing is, instead of tuning the phonons to soften by sort of changing parameters of the static Hamiltonian, here we're trying to tune ourselves to kind of instability and soft phonon regime using non-equilibrium process. Okay, now what I gave you some kind of scenario, but it's not clear what it has to do with real materials. So let me say right away that we did not look at the actual physics of Bucky-Bose superconductors, because it's complicated. You have to deal with 3 electron bands. Our philosophy was, if for this effect to be important, it has to be universal. Therefore, let's try to sort of take some sufficiently simple model, but not sort of concentrate on the exact details of Bucky-Bose superconductors. So one of the important aspects of Bucky-Bose superconductors is that the pump light does not cover directly to phonons, which are responsible for superconductivity. This light couples to phonons, which have matrix element. This is this infrared active phonons. But it's believed that these infrared phonons have sufficiently strong coupling to Raman phonons, which are responsible for superconductivity. So therefore, light excites infrared phonons excite Raman phonons, and this then excite sort of gives rise to this superconductivity. So we'll look at the problem starting from here. So we'll assume that these infrared active phonons have been excited, and they are now some kind of like a classical source of drive, right? We'll not solve the whole problem. We'll just go from here down, right? We'll just look at a single type of phonons, which is this Raman phonons, which give rise to electron coupling and electrons. And we'll also neglect things like, that there may be some static renormalization of electron-phonon interaction, which is, say, what Anton George has been working on. We'll focus on really, truly dynamical phenomena. Okay, so this is just to give you a flavor of what we're dealing with. So we take the simplest model of electron-phonon interaction, again, just like in the BCS model, right? BCS model is based on the simplest type of Holstein type Hamiltonian of electron-phonon interaction. We don't put the actual band structure, LDA calculations. We start with a toy model. That's the philosophy which we have here. So we just have fermions. Okay, it's somewhat, okay, details are not important if people are not familiar with this kind of Nambu notation. So we have this as electrons, these are phonons, and this is some phonon frequency. But we have phonon nonlinearities. And the reason this is important is it's known that superconductivity arises from phonons in the entire Brillouin zone. You really need phase space for phonons in order to mediate pairing, whereas light couples only to phonons at q = 0. Therefore, we have to transfer our drive from q = 0 to finite q phonons. And that's achieved by having phonon nonlinearities, right? So in our case, you can say that there are 2 nonlinearities. We excite infrared phonons at q = 0. By symmetry, they can only couple to Raman phonons at q = 0. But then Raman phonons at q = 0 can couple to Raman phonons at finite q. And you can see how this is coupled just by looking at the lowest order terms, right? Let's say I have replaced this 3, in the third power of the phonon field, I have expectation value of q = 0 phonon, and then it couples to phi square. And now you can immediately recognize that this becomes exactly just like parametric drive that we discussed before. So as long as I have, as I think, if I induced oscillation of my infrared phonons, then they induce oscillation of my Raman mode at q = 0. This will provide parametric resonance of phonons at finite q, and therefore this argument is regardless of what kind of linearity I have, it can be cubic or quartic. So that's the mechanism of how I actually get parametrically driven Hamiltonian for my phonons, which is discussed, can enhance electron-phonon interaction. Well, actually, it turns out that life is not as simple. So I'll skip sort of rather tedious, although kind of very interesting calculations. I'll just show you the result, what makes the problems much more subtle. So this is a so-called RPES. So this is more or less like the spectral function of electrons, which tells you more or less, so for a given momentum, at which energy you can find an electron. And so what you see here is like this. So this is a dispersion. Like we see that the energy changes as a function of momentum. So this is the king. That's a very famous feature in electron-phonon systems because it shows you that you have strong electron-phonon interaction. What's important to us is also that at omega equal to 0, this is before the drive, before we switched on the drive, you see we have a very narrow line width, which means we have very coherent electrons. And that's what we usually do in the theory of superconductivity. We neglect finite lifetime of electrons, which is completely justified. And then we look at what happens as the system is driven out of equilibrium. So you can see that electron-phonon interaction is enhanced. Okay, it may be hard to see from this plot, but so here this is like basically a measure of the slope. So the slope is basically, it's a measure of the effective mass. And if electron-phonon interaction gets enhanced, this means that electrons are dressed more strongly by the phonons, so the mass goes up. And indeed, we can see that there is an appreciable change of the electron mass, which is what we want, right? So electron-phonon interaction has gone up. But there is also an unpleasant effect. If you look at the line width, it actually gets broader. So it turns out that when we make a non-equilibrium state of phonons, it's not only the good thing that we get, which is enhancement of interaction, we also get a bad thing, which is electron becomes less coherent. And if they're less coherent, it's harder for them to make this kind of very coherent BCS state, which evolves on very coherent correlations of Cooper pairs. Therefore, we have to do very careful analysis of the competition of these two phenomena, enhancement of electron-phonon interaction and suppression of superconductivity. So the way one does it, again, one kind of solves, if you remember your basic solid-state classes, kind of self-consistency condition on the BCS gap, right? It's an order parameter, and you want to find the first temperature at which this is possible. And that's exactly what is done. So this is a so-called Migdal-Eliashberg formalism. So you calculate at a certain eigenvalue. When this eigenvalue becomes negative, it's an indication that you can now find a solution to this equation, that superconductivity is possible. And so what we find that in this case of driven systems, something interesting happened. So as we start driving, this eigenvalue sort of starts getting small and becomes negative, which means, oh, superconductivity is now possible, right? So we enter in the superconducting state. But then something quite dramatic happened. Instead of sort of continuing to be negative, it just shoots up. So if we neglected heating of electrons, right? If we only looked at the increase of electron-phonon interaction, we would have, wonderful world where we could just stabilize superconductivity for a very long time. Unfortunately, the reality is such that superconductivity exists only as a transient state. At first, electrons kind of benefit from strong electron-phonon interaction, but then they discover that it's just too much heating happening. They become very incoherent, and superconductivity actually becomes even less favorable than it was to begin with. And that explains why in experiment they could also see it as a transient state. So, okay, this probably, I can. So you can then calculate, let's say, what you expect as an increase in TC. And we find that in the simple Holstein model, we can get an increase of TC by something like 150%. So it's not the same huge factor as what they saw in experiments, right? It was a factor of 5. But again, we took the simplest Holstein model. Like presumably, if we take all the details of buckyball band structure, all the details of electron-phonon coupling, we can get something which is different, hopefully larger. But for us, it was just important as a proof of principle. Okay. So, so this was example from the world of solid-state physics. Now let me switch to kind of ultra-cold atoms. So this work really kind of is based in collaboration with Jörg Schmidmeyer's group. And actually, motivation for this came from high energy. In particular, when people looked at heavy ion collisions, they noticed something quite peculiar. Sorry, I skipped the slide. That actually the system, like soon after the collision, the system seemed to very rapidly come to a state which didn't look like a true thermal equilibrium. So somehow, when we read standard textbook on statistical physics, they tell us, okay, make a non-equilibrium state, and then during some microscopic timescale, it relaxes to a true equilibrium, right? It just explores all the available phase space. Whereas what was seen in experiment looked more like there was some intermediate transient state in which the system reached very rapidly, and then it stayed there for a very long time. And that actually motivated a fair amount of theoretical work in the group of Christoph Wetterich, where they sort of started with some field theories, just like from basic field theories, but then also with sort of something more realistic. And they coined this term of prethermalization, so where the system doesn't go to a true thermal equilibrium, because usual thermalization tells us that what should happen is that the system forgets all the details of the initial state, right? It only remembers about initial energy, right, which is converted to temperature, maybe some integral of motion, like the number of particles. But details don't matter. Whereas what comes out from this theoretical analysis is that the system gets stuck in some state which depends on your initial state. And it's not a true thermal equilibrium, and it's not something, and it's truly kind of a many-body phenomenon. It's not just because, if in a discrete system, of course, you have discrete levels, so it will not be surprising that you are stuck in one certain superposition of eigenstates. So that's the kind of question that actually we want to think about using the toolbox of atomic physics. So this is roughly the kind of experiment that we'll be talking about. So the kind of running ahead of myself, what I want to show you is that this prethermalized state, this very strange type of dynamics where you go not directly to thermal equilibrium, but to some strange long-lived state, is something that you can realize with cold atoms. And the system is as follows. So we have one-dimensional condensate, which is shown here. And OK, I'll spare you the details of how it's done using, how you get, I don't know, let's say microkelvin kind of BC on top of the kind of essentially room temperature semiconductor. But we have this trapping potential. And what the group of Jörg Schmidmeyer can do is they can split one condensate longitudinally into two. So it's basically splitting along this long axis, right? So you have one cigar, and then you split it into two cigars. And then what they do, they interfere these two cigars. So let me take you sort of back a few years and explain why interference experiments are an interesting probe. So actually, this was one of the first probes that people used with ultra-cold atoms. So they prepared a pair of independent condensates, and then they let them interfere and looked at interference fringes. So the type of experiment that David does with polaritons. And the question was, well, why do we see interference fringes if these condensates have been prepared independently, so they don't have a well-defined relative phase, right? Because naively, okay, we have to have coherence in order to see interference fringes, but here there is no coherence. So the idea was that, well, somehow by doing the measurement, we sort of establish a coherence. Or said differently, that in every shot we see interference fringes, but we don't know what the position of this interference fringes is. Okay, I'll show you later how to, like more quantitatively, how to think about this. But at least in these first types of experiments, these were really macroscopic condensates, so there was nothing. Basically, this kind of nice interference fringes just demonstrated macroscopic quantum coherence. But then kind of the groups of Jean Dalibard started doing experiments with 2D, where they started doing it with two-dimensional condensates where fluctuations were enhanced. And so now interference fringes did not look like straight lines, but they actually see that there is kind of this very strong meandering. Right, so this very strong meandering shows you that the phase between the condensate is not constant, but it actually varies from point to point. And that's an indication of strong enhancement of fluctuations in 2 dimensions. And again, this is a group of York-Schmidmeier. So these two condensates, but now prepared independently. So it's not a dynamical experiment. This was equilibrium. But when they do interference fringes, they also see this interference fringes which are not straight, but have a lot of meandering, which means that there were many thermal and quantum fluctuations in the system. So how do we think about interference experiments? Let's start first with macroscopic condensate. So you have atoms in macroscopic condensate 1, atoms in macroscopic condensate 2. Then we let the atoms expand and we measure. Right? So our measurement means we measure the density, and density is a square of the wave function. So let's just think about it. So when we think about the wave function of atoms, after the expansion, it's a superposition of wave function of atoms coming from the first condensate and the second condensate. And then the interference part is just like the cross term in the density. And if you do very simple algebra, if you relate these atoms, this wave function, right? This is just free expansion. Atoms expand, completely ballistically. So we can relate the wave function of the atoms after the expansion to the wave function before the expansion. We find a simple relation that interference part of the density, it has this oscillatory term. The wave vector is determined just by some geometrical factor, like the distance between condensate masses, expansion time. And then there is also the phase difference. And of course, this phase difference is completely random, right? And so, but what does it mean that it's random? So again, I remind you that in quantum mechanics, if we take an average, what it really means is doing an experiment many times and taking an average, right? And so what this means is that if we do this interference measurement many times and we see this interference fringe, but then we would have to sum up all the interference fringes. And if they're all shifted with respect to each other, these kind of patterns will wash out, right? And that's exactly consistent with our expectation that if we take expectation value of this operator and relative phases are random, we'll get 0. But we're not talking about doing many measurements. We talk about making a single measurement, right? And when you do a single measurement, you can think about it as, so we don't know what this phase is, but what we do know is that whatever this phase is, if I see a maximum at a certain point, then I'm guaranteed that there will be another maximum a certain distance away, right? So you can think about it also in the language of correlation functions. Okay, but this was kind of macroscopic condensates. Now we can talk about something more exotic, which is one-dimensional condensates. What's more interesting is that in one-dimensional condensate, as we said, the phase is not the same, like along the condensate, which means that as we look at interference, and in this experiment, most of the expansion of atoms occurs in transverse direction, because atoms were so strongly confined that they mostly flew out in this transverse direction. So this kind of relative phase at point R1 will correspond to interference fringes, like with this position of the maxima. We looked at a different point, the relative phase is different. Now we have different position of the maxima. So if we try adding them all up, we get kind of a reduced contrast. So we get this meandering fringes, which means that if we sum them all up, we get a strong reduction of coherence fringes. So it's a bad interferometry. But it's also interesting that now if we try to integrate this kind of interference fringes over a certain length, then it becomes kind of an integral of, and if you go through the calculations, you can show that it becomes an integral of the correlation function. And in fact, you can calculate, as you remember in your basic quantum mechanics, you can, when you measure, right, just think about a single particle wave function, right? Let's say this is your psi squared. So you can talk about the average value of x, right, which is integral x psi of x squared dx. But you can also talk about, let's say, x squared average, right, x squared psi of x squared dx, and so on. And the wave function itself is like a histogram, right? If this is your x, oops. So if you do measurements many times, then let's say you have a certain probability to find a particle here, you have a certain probability to find a particle here, and once you did many measurements, you get a full histogram, you get psi squared from which you can reconstruct all of the moments. So the same is here. We have a classical measurement and a quantum mechanical wave function, and we can talk about it using kind of different moments of the kind of this amplitude of interference fringes, or just using distribution function of the fringes. So that's roughly the way the experiment is done. So, okay, this was interference pattern. In this case, it's a particularly good one. We see straight fringes, right? So we can extract the position of the maxima, right? It's the phase, and we have the amplitude, which is contrast, and then we can plot, you know, this as a point, right? We have a phase, and we have the amplitude. So that's one measurement. Then we do these measurements many times, and we get a distribution function. We can talk about distribution function of both the contrast and the kind of the absolute value and the phase. Okay, so to make a long story short, when we talk about non-equilibrium systems, it turns out that we can calculate the distribution functions really well. They're kind of interesting. They so they have very asymmetric shape, but okay, this is just a point that we can, like from first principles, you just give us atoms with the interaction, we can understand what this equilibrium distribution functions should be. And this agrees with experiments. But as I said, so yeah, here just to point out that these green lines, this distribution function are measurements, like from Schmidt-Meyer's group, and this red lines is theoretical calculations, again, no fitting parameters, but just some uncertainty due to fluctuations in the density of the atoms. But our emphasis is more on non-equilibrium, right? So I just told you that if I have two condensates in equilibrium, I know how to understand its interference, but what about non-equilibrium? So now we're looking at a process when we had one condensate, it was split into two. So we had a lot of phase fluctuation in the condensate to begin with, but when we split it into two, the same, every atom goes into a superposition of being in the upper cigar and in the lower cigar, and therefore the relative phase is really zero, right? So whereas individual phases are fluctuating, but they're still fluctuating in phase. But now that they're decoupled, their kind of fluctuations proceed differently. So we start getting an increase of relative phase fluctuation, right? So the interference fringes would go from being straight to being more meandering. And then eventually we expect that the system should thermalize, right? So somehow our interference fringes should be exactly the same as what we get when we prepare two condensates separately from each other, right? Because that's what we expect. So two systems, like a system driven out of equilibrium, should reach its thermal state. Well, actually, so this really came as sort of first theoretical idea that this should not be true, and I can just give you the gist of the idea. So it turns out that when we talk about interacting bosons in 1D, they're kind of like phonons, or like some hydrodynamic fluid. So what matters to us is we can introduce a relative phase, can introduce fluctuation in the density of atoms in the two condensates, and we can write an effective Hamiltonian which approximates very well this kind of interacting system, right? Because clearly it's kind of the same way as when you have ions, like phonons describe quite well vibrations of the ions. So in 1D, it actually turns out to be also true for the fluid phase. And therefore, well, here you can immediately recognize either your hydrodynamics or your phonons, and you can diagonalize this by, again, going to momentum space. We just get harmonic oscillators for different momenta. And then our initial state for every one of these harmonic oscillators is very peculiar. It has very small uncertainty in the phase and very large uncertainty in the number of particles, right? Because when we split the atoms, we're very likely to get large number of fluctuations, like because every atom is being in superposition of being in the two wells. But now every one of these harmonic oscillators start to evolve, right? Because if you make a squeeze state of harmonic oscillator, it starts rotating. But as we said, these are like phonons. They have a linear dispersion, and therefore this oscillation for different wave vectors occur with different periods, and they get out of phase with each other, and somehow we have to sum over all of them. But another kind of curious observation is that most of the energy in the initial state comes from the fact that, again, we said that think of harmonic oscillator, right? So if you squeezed it in one of the directions, then you have large fluctuation in the number of particles, right, n of k, and therefore that's what really carries all of the energy. But then this extra energy is actually does not depend. As long as every atom is just entangled with itself, we find that every mode, every phonon mode gets the same energy. So that's something that we're used to in statistical physics, equipartition of energy. But in this case, that's just an artifact of coherent evolution, right? We get equipartition of energy, but this has nothing to do with true thermal equilibrium. It's a result of unitary evolution. Yet what it tells us is that when all the modes will dephase with respect to each other, what we should see is just kind of the energy per mode, but this energy per mode is the same. Therefore, the system should look as if it has some effective temperature, but this effective temperature is just set by the interaction and not true thermal equilibrium. And indeed, so this is what was then measured. So this shows you this. Remember, I told you about distribution function. So this is really like you take a quantum mechanical observable, and instead of measuring individual moments, you take the entire wave function. So this is now a way of characterizing these interference fringes through these histograms. And what you can see is that if we, at long times, right, so if we look at long times, so we can ask, right, so, okay, right, so this is actually as time progresses, we can ask whether the system is in thermal equilibrium with the temperature that you would expect. But if, we know that for system in thermal equilibrium, we can calculate this distribution function really well. So if we take the true thermal temperature of the system, so then we should get this blue line. If, on the other hand, we get this effective temperature, which just comes out of equipartition of energy, we get the red lines. So we see that the system actually is not described by the true equilibrium temperature, but it's described by this effective temperature, which emerges, which comes entirely from the interaction. We can, let's say, compare theoretical prediction of the effective temperature. And so this temperature turns out to be a factor of 8 smaller than the true equilibrium temperature. So the system is stuck in some weird state where for the relative phase, the energy density is 8 times smaller than it should be, and it lives there for a very long time. Well, in reality, so there is some kind of drop in the contrast, which means that this effective temperature seems to increase in temperature. But it appears that this is just to the fact that, okay, it's still, we said that these systems are almost isolated, but not ideally isolated. And that sort of is very close to being kind of residual heating. So if we could make it even better isolated, then this effective temperature would stay almost constant as a function of time. Okay, I guess, yeah, I only have a few minutes for the last part. Okay, maybe at least just give you a flavor of what we're thinking about. So now let me, again, continue with cold atoms, but switch from bosons to fermions. And here the idea is that we want to look at the Fermi Hubbard model. I'm sure you've all seen this motivation that we have this kind of very intriguing materials like high TC cuprates, which we're trying to understand, and we want to make a quantum simulator by putting fermions in optical lattices. So we have, again, orders of magnitude difference in energy scale, but very similar underlying Hamiltonian. So what has happened in the last few years is development of a new tool, which is atomic microscope. So it's a way where you can look at a many-body system of fermions and really tell what's happening on every site. So these microscopes have been realized in several groups. So this specific data set is from the group of Immanuel Bloch. And these are measurements in 1D, and they can tell like whether a given site has no atoms, it has spin-down atom, spin-up atom, or 2 atoms per site. So it's kind of like a theorist's dream where you have a many-body wave function and you know what's happening on every site. And okay, so like these microscopes have been done to do very exciting measurements. Say Marcus Greiner's group measured kind of essentially the onset of long-range antiferromagnetic order in 2D. And again, notice that their measurements go beyond what we're used to in condensed matter. In condensed matter, we just measure two-point correlation function. That's what neutron scattering does for us. Whereas they can measure full distribution, like it's again a full histogram of the Néel order parameter, just like here, right? We're not just averaging, say, the first moment or the second moment. We're measuring all the moments by calculating full distribution function of the Néel order parameter. And there are sort of very strong differences between true quantum ground state and our kind of classical picture of Néel order, which is pointing in a random direction. And then in 1D, there was beautiful work by Emmanuel Bloch's group. So this connects to the physics of spin charge separation in 1D. So for people who haven't heard about it, let me sort of give you kind of again a physical picture. So in 1D, you cannot, like, you start at half filling, you have an antiferromagnetic Heisenberg model. So you have spins which want to make singlets. However, you cannot have a classical antiferromagnetic state. So it's just forbidden by symmetry. As a result, the system makes this kind of weird state where you have spins bound into singlets. They're not necessarily nearest neighbor singlets. They can be somewhat longer range, but they decay fairly rapidly with distance. But every fermion with a spin has a partner with the opposite spins. They're all parts of a singlet. So now what happens if you remove one of the sides, right? We have taken a fermion out. Okay, we have an empty site here, but in addition, we now have an unpaired spin, right, which was part of the singlet. And then what happens to this hole? So now we have a kind of a site which has charge, and we have a site which has a spin half excitation, because everywhere else we have charge 1 and all the spins bound into singlets. So in 1D, this kind of charge and spin can separate. So and that's what we call a holon, right, which is a hole surrounded by spin singlets, and we have this unpaired spin half. And well, that's really kind of the cartoon picture of spin charge separation. And that's already kind of very remarkable picture, because it shows, it requires that, you know, if you look at sites which are two lattice constant away from each other, if they were part of the antiferromagnetic, like if we were looking at antiferromagnetic configuration, you know, when you are two sites away, you expect ferromagnetic correlations. If, however, we have a hole, and then the singlets mostly go around this hole, therefore correlation between these two sites should be antiferromagnetic. But indeed, in 1D, one can use beta ansatz to make an even stronger statement. If we take a wave function which has holes in it, but then we remove all the holes, so this is a so-called squeezed space, and we just look at the part of the wave function which has spins, then the spin part of the wave function will be exactly the same as if holes were not there, as at half filling, right? So, of course, it was always considered to be kind of like a theorist type of idea, because in order to do, you cannot do this in real solids, because I mean, you would have to know what's happening on every side, but that's exactly what quantum microscopes can do, because they get information about every site in a chain. So this shows you spin correlation functions as a function of distance, sort of regardless of whether there are holes between them or not, right? And then now, and different colors correspond to different doping levels. So let's say this is half filling, and you can see that, okay, we have antiferromagnetic correlation on neighboring sites, then ferromagnetic, basically this structure when we have two lattice constant, and then they can oscillate and decay. But as soon as we start introducing holes, you see that this kind of pattern is washed out very rapidly. The red line, right, is 30% doping. Then we have 60% doping, the blue one. Okay, it's basically gone. But now they take the same doping levels and seem to look at squeeze space by removing all the holes. And you see that the correlation in spin space remain the same. So that's sort of a direct proof of spin charge separation. And so, okay, but 1D is exactly understood. So what do we want? Where do we want to take it? And the idea is, well, we want to take it to 2D. And we want to look at magnetic polarons in 2D. And in the case of magnetic polarons, it's a very, okay, let me maybe just take you through the bottom line. So when we think about a spinon and a holon, unlike 1D, they cannot completely separate. They're actually bound, right? So they behave just like quarks and QCD, which are bound by a finite, by a string. But instead of the quarks in this case, this can be formulated in terms of frustrated magnetic interactions. Okay, and but so again, what's interesting in high energy physics in QCD is, and we can take the same two quarks and they can make bound state a different angular momentum. So there is a kind of, the lowest energy state is angular momentum 0, but then there are also bound states at finite angular momentum, right? And they actually call them even completely as different particles. So the same should be true when we talk about spinning and holons. So they are bound, when people talked about the Fermi Hubbard model, all the discussion so far focused on a state with angular momentum 0, because that's the only one which is relevant for the ground state. But when we talk about driving the system out of equilibrium, you can also make excitations which correspond to finite angular momentum. Just like we have mesons, which have finite angular momentum states in QCD, we can get finite angular momentum states of spinning and holon pairs. And this is something that one can also be probed with modulation spectroscopy, something very similar to what David worked back at Harvard in order to observe this kind of very special resonance states. Okay, with this, let me just conclude. I tried to give you an example of some of what I think are very interesting phenomena in non-equilibrium dynamics, how we can control states of matter in solid state physics, how we can see this very interesting non-equilibrium state, which, however, very long-lived. This is prethermalization, and then how we can use dynamics as a probe of some exotic states and kind of as a test of maybe microscopic, the right interpretation of strongly correlated systems, such as a Parton model of polarons. Thank you.
About the second part. So, as I understand, the skin is about a quench process, not like a floating-driven process. So, what's the controlling mechanism for the system to stay in the prethermal state?
So it turns out that in this case, it's very close to being integrable, because you see this effective description that I showed you, Luttinger liquid, right? It's just harmonic oscillators.
Okay.
So it's proximity to being an integrable system that allows this prethermalized state.
So you show a figure saying that if the separation if you have a better separation, then the system will stay in the prethermal state for longer time.
Right. Actually, I don't have a plot. So your claim that when they improved the apparatus, so I showed you that this effective temperature kind of was rising as a function of time. He says that, okay, if they isolate it better, they can make it much flatter, right? That it's almost stayed the same. That this is kind of this heating is not intrinsic to this many-body system. That appears to be just some kind of residual shaking of the apparatus.
Maybe one last quick question.
In the case of the photo-induced superconductivity, you had these parametrically amplified phonons.
Yes.
I can solve that equation. That's a Mathieu equation, and I can quantize in terms of those Mathieu wave functions.
Sure.
Now, when I calculate the effective potential between the fermions, it's going to be a function of T and T prime. It's going to be something non-local. So how do you make an effective interaction of the delta?
So that's exactly what I solved. We solved the full Floquet McDowell Eliashberg theory.
So it's a non-integral integral equation in time as well.
You have to, right? So there is retardation effect. So it's actually even more complicated. You know, when you have non-equilibrium process, let's say all the Green's function becomes a function of 2 times. And usually you sort of give the following argument. You say, oh, I separate into kind of a center of mass time, T1 plus T2 and T1 minus T2. And my T1 plus T2 has slow evolution, and T1 minus T2 is fast, and I do Fourier transform. In this case, you cannot do it, because you're driving at a frequency which is very fast. So therefore, what you have to do, you have to as a function of the center of mass time, T1 plus T2, you have to separate different Floquet components. And then amplitude of those Floquet components, they become smooth functions of time. So it's actually a trick that electrical engineers use, because they also have to do data transmission. And Nirtash's kind of undergraduate degree was in electrical engineering. So that's the way we do it. So therefore, what we do is kind of looks somewhat similar to the usual non-equilibrium, where you have sort of this slow center of mass time and the relative frequency, but we have an extra index, which is this Floquet component. But yes, it was part of the analysis.
All right, let's thank Eugene again. So, Eugene, for this...
Good seeing you. I'm going to take off. Good seeing you again.
For this out of equilibrium superconductivity, if you connect electrons to a heat bath, can you cool them fast enough to where you get continuous enhancement of superconductivity?
Question. I don't know. This would be very tempting. If you could simultaneously provide enhancement and cooling of electrons, yes, this would be a way of doing